Hey there, Mr. Sutton here with the AB Calculus 4.2 Extra Practice Number 4 solutions on increasing and decreasing intervals. For this problem, we're trying to find increasing and decreasing intervals for this polynomial. Let's start by getting the derivative and finding critical values. So we've got 3x squared minus 3, and then let's set that equal to 0 and solve. First thing we can do to solve this, a lot of ways we could go here. I'm going to factor out a 3, so that leaves us with x squared minus 1. And then, let's see, x squared minus 1, if I add 1 in square root, we've got x equals plus or minus 1. So those are going to be our two critical values. Let's set up a number line now. We've got an f prime line here. Critical values at -1 and +1. Let's do some sign analysis around those. So on the far left interval, let's test something less than -1, like -2. Plugging that into this factored version, well, 3 is always positive. -2 squared minus 1, that's going to be a positive. And then testing something between -1 and 1, like 0. Plugging that in, we've got a positive times a negative, so that's negative. And then finally something bigger than 1, like 2. Plugging that in is going to give us a positive. Since f prime is positive in the first and third intervals, that means that f is going to be increasing from -infinity to -1. And from 1 to +infinity. Since f prime is negative on this middle interval, that means f is decreasing from negative to +1. On this one, we're trying to figure out where this function is increasing or decreasing. So let's start by getting some critical values. Before I can take the derivative, though, let me rewrite this as 2 parentheses x squared plus 1 to the -1 power. And then I can just use the power rule with the chain rule instead of using the quotient rule. So this is going to be -2 times x squared plus 1 to the -2 power. And we're going to multiply that by the inner derivative of 2x. And I'm just going to rewrite this as a fraction so it's easier to work with. So that'll be a -4x over x squared plus 1 squared. And now I want to figure out where this either equals 0 or does not exist. So let me set this thing equal to 0, and this whole fraction is going to get zeroed out wherever the numerator, 4x, has a value of 0. So I could call that either 4x or -4x. Either way, at x equals 0, the numerator is zeroed out, and thus the entire fraction. Now, how about places where this fraction does not exist? Well, looking at the denominator, you've got x squared, which is always going to come out either 0 or positive, and you're adding 1 to that, so you're never going to get a 0 out of the denominator. So there's no critical values for this thing being undefined, only for the fraction equaling 0. So let's go ahead and plot that on a number line. Here's an f prime line, and we have 0 as the only critical value on here. Now let me test something in each of these intervals. So to the left of 0, let's try out -1. Now as you're doing your sign analysis, the denominator is always going to come out positive. I mean, you're squaring the inputs, you're adding a number, you're squaring again. There's no way you're getting a negative out of that denominator. So it's really up to the numerator. And don't forget, we have this negative out in front. So if I make the numerator negative by plugging in -1, this negative out here cancels that to give me a positive. And then something bigger than 0, like 1, if I plug that in here, I'm going to get a positive up here, but the whole thing becomes negative. So since f prime is positive to the left of 0, we can say f is increasing from -infinity to 0. And since f prime is negative after 0, we can say that f is decreasing from 0 to +infinity. For this one, we're trying to figure out where this function's increasing or decreasing. Let me start by taking the derivative. So that's going to be 2/3 x plus 1 to the -1/3. And let's see here. We're multiplying by the derivative of the inner function, but the derivative is just 1, so we don't worry about that. So let me just rewrite this now in rational radical form, so fractions and roots, and then I'll figure out critical values after I've done that. So I'm going to have a 2 in my numerator. Downstairs, I'm going to have 3 times the cube root of x plus 1. And I want to see where this is either 0 or undefined. Well, since I've got a constant in the numerator, there's no way to make this 0, so it can't be 0. However, we might still get critical values where this is undefined. Since this is an odd root, we don't have to worry about taking the root of a negative number. However, if we have a 0 in the denominator, that's still going to mess things up. So if we plug in -1 for x, that would zero out our denominator. So our derivative then, f prime, does not exist at x equals -1, and this gives us a critical value that we can do some sign analysis around. So let me put that on my number line here, f prime line. We've got -1, and let me test something to the left of that, like -2. If I plug -2 in here, well, that's going to make the stuff inside the root negative. That's going to negate the entire denominator because an odd root just keeps the sign of whatever you're rooting. And because the numerator is automatically positive, a positive divided by a negative gives us overall negative result. Next, let's plug in something bigger than -1. I'm going to be lazy and use 0. I always do when I can. So that's going to be the cube root of 1, which is positive. That keeps the denominator positive, making the whole fraction positive. So that's a positive result. Since we are positive for f prime over here, that means that f is increasing from -1 to infinity. Since f prime is negative over here, that means f is decreasing from -infinity to -1. For this polynomial, I want to know where this thing is going up or down. Let me do this calculus style by taking the derivative and finding some critical values. Using my power rule from left to right, we've got 3 times 2/3, which is 2x, and then a square there. Then we have 8x plus 6, and that -1 is just a 0, so we don't care about it. I'm going to set this equal to 0 now and find critical values. I can start by taking out a 2 from everything. So that's going to be x squared, 4x, and 3 left inside. And then this looks pretty easy to factor. Things that multiply to 3 and add up to 4. We've got x plus 1 and x plus 3. So setting each of these equal to 0, we see this equation is true when x equals either -1 or -3. So those are our 2 critical values we're going to test around. Let me make a number line here, little f prime. Here's -3, here's -1. And now let's test something in each interval, and I'll just use this factored version of f prime to do the sign analysis. So let's test -4 to the left of -3. That gives me a negative times a negative, which is positive. Next, we test out, let's try -2 in here. That's going to be a negative times a positive, which is negative. And finally, let me test out 0. That's an easy number to the right of -1. That's a positive positive, gives me a positive. Since f prime is positive in the first and third intervals, that means that f is increasing from -infinity to -3, and from -1 to positive infinity. And since f prime is negative in the middle here, that means f is decreasing from -3 to -1. For this trig function, squared trig function, we're trying to figure out where this thing is increasing or decreasing on the interval from -pi to pi. So we'll start by taking the derivative and finding our critical values. Derivative here is going to require the chain rule. Our outer function is something squared, so the derivative of that is 2 times the something to the first, so 2 times sine of x. But then we have to multiply by the derivative of sine, the something, and that's cosine, so we have a cosine here. Now there's a few ways to solve this. First off, I'm going to set it equal to 0, but now once you've done that, one way to solve this is actually a double angle identity. You could turn this into sine of 2x and solve it that way. Or you could figure out what makes sine of x equals 0 and cosine of x equals 0 individually. That's what I went. That's the direction I went because it doesn't require any special identities. But there were options on this. So we can say sine of x equals 0, and we're just looking between -pi and pi. Sine of x is going to be 0. The y value on the unit circle is 0 at -pi, at 0, and back at +pi. So anywhere where you're on the x-axis. Now cosine, if we zero that out, we've also solved the equation. So cosine of x equals 0 on the y-axis, specifically in this interval on -pi/2 and +pi/2 at the bottom and the top of the unit circle. So let's make a number line and do some sign analysis. Here's my f prime number line. And because I have endpoints here, I'm going to include those on the number line. So negative and positive pi, just so I know not to test anything to the left or the right of those numbers. Now in between, we've got a couple critical values. The first one is this -pi/2, followed by 0, and then pi/2. All the other critical values also happen to be endpoints, so we don't really worry about them. Let's test something on each of these intervals now. And I'm going to be using this function right here, the sine cosine function. So testing something between negative pi and negative pi over 2, probably the easiest way to think about this, if you're between negative pi and pi over 2, you're between the left and the bottom angles on the unit circle, you're in quadrant 3. So if you plug anything in quadrant 3 in here, that's going to make sine negative because you're below the x-axis. It also makes cosine negative because you're to the left of the y-axis. Negative times a negative gives me a positive. Next, between negative pi over 2 and 0, well, that's actually quadrant 4. So if you plug in quadrant 4 numbers, that makes sine negative, cosine positive, overall negative result then. Between 0 and pi over 2, that's quadrant 1. That makes both of these positive, so this is a positive. And between pi over 2 and pi, that's quadrant 2, between 90 and 180. So that's going to make sine positive but cosine negative, so we're negative again. Because my f prime is positive on the first and third intervals, that means f is increasing from negative pi to negative pi over 2, and also union 0 to pi over 2. And because f prime is negative in the second and the fourth intervals, that means f is going to be decreasing from negative pi over 2 to 0 and from pi over 2 to pi. On this one, I'm trying to figure out where this function is increasing or decreasing. Let me start with a derivative and critical values and all the rest of that. So derivative, we've originally got something to the 1/2 power. So derivative of that using the chain rule, we're going to have 1/2 times something to the negative 1/2 times the derivative of the something times negative 2 in this case. Let me clean this up a little bit because in a sec I'm going to solve for where it's 0 or undefined. So I want to put this in a fractional radical sort of form to make it a little easier to solve. So simplifying here, negative 2 and 1/2, that reduces to just negative 1 on the outside. And then this whole parentheses of stuff is moving downstairs to be square rooted. So I've got negative 1 over the square root of negative 2x plus 6. So I want to figure out where this fraction is either 0 or undefined. Well, we have a constant numerator, so we can't make this 0. However, this is going to be undefined if x equals 3, and since this is square root, honestly, if x is anything bigger than 3, that's also going to give us trouble because you're going to be square rooting a negative at that point. So if x is going to be, or f prime is going to be undefined, DNE, for x greater than or equal to 3. So we're going to make sure we don't plug in any numbers there. So 3 is kind of the border. So then, confining our explanation to the values where x is less than 3, for those values for which this is actually defined, what does the sign analysis look like? Well, here's the other cool thing about this one. I mean, it's been kind of annoying up to this point with all these undefined spots and radicals and fractions, but here's the neat part about this. The square root function can't give you anything back except 0 or positive, and we don't want 0. We're excluding 0. So really, this square root's only going to give you back positive numbers on this interval of x values. The numerator is only going to be positive because it's a constant. So you have a positive over positive, and this whole fraction has a negative in front. So this whole fraction for x values less than 3 is always going to come out negative. F prime is always going to be less than 0 on this interval. Therefore, that means that since f prime is always negative, we can't be increasing anywhere because f prime is never positive. But we are going to be decreasing for all the values to the left of 3. So from, we'll say, negative infinity to 3, that's going to be our one decreasing interval. On this problem, we're trying to analyze this function to see where it's increasing or decreasing. Let's start by taking the derivative and finding some critical values. And even before I do that, I'm going to rewrite this 4 over x as 4x to the negative 1. A little easier to use the power rule now. So using that power rule, our f prime is going to be 1 minus 4x to the negative 2. And I'm going to clean this up and combine terms a little bit just to make it easier to figure out where it's either 0 or undefined. So I'm going to rewrite this as 4 over x squared. And I'd like to get this all in one big fraction because it's hard to deal with things piecemeal here. So I can think of this 1 as really being an x squared over x squared. Combining with this, we're going to get x squared minus 4 all over x squared. And now I want to figure out where this is either 0 or undefined. So let's set it equal to 0. And if I'm talking about 0, if x squared minus 4 equals 0, then that means that x has to be, if we add 4 and square root, x has to be plus or minus 2. So those are two critical values we can take to the bank. But now we have variables in the denominator. If I plug 0 in for x, that's going to make the bottom 0. So we can say f prime does not exist at x equals 0. This gives us another critical value that we have to test around. So in total, that's 3 critical values to put on our f prime number line. So let me do them in order. We've got -2, 0, +2. And now I have to test a number in each interval. I'm going to use this fraction form of the derivative. A little easier to see what the signs are doing in this one. So testing something less than -2, let's test out -3. Now, one thing to keep in mind as you're doing the sign analysis to save a little bit of time, the denominator, you're squaring the input, so the denominator is always going to come out positive no matter what. So we can pretty much ignore that denominator and focus only on the numerator. The numerator is going to decide what the sign of the whole fraction is at this point. So if I plug in -3, that's going to be 9 minus 4, which gives us a positive. Plugging in a number between -2 and 0 now, let's try -1. That's going to be 1 minus 4 up here, which is a negative. And plugging in a number between 0 and 2, let me try +1. I get the same result up here. That's just 1 minus 4 again, which is negative. And now plugging in a number bigger than 2, like 3, gives me the same result as -3. 9 minus 4 is still going to be positive. That has not changed in the last 30 seconds. So since my f prime is positive on these outer intervals, that means that f is increasing from -infinity to -2 and from 2 to +infinity. Now since f prime is negative on these inner intervals, that means f is decreasing from -2 to 0 and from 0 to 2. And unfortunately, we can't include 0 and just write -2 to 2 because in the original function, 0 makes the original undefined. So that's not going to be part of any interval, no matter what your philosophy on including border values is with increasing, decreasing intervals.